All right. Welcome everyone. I'm Ram Nivas Indani. I work in Android Core Graphics team at Google, and we'll be talking about ARR on Android, adaptive refresh rates on Android. We'll walk through some examples how Android does the refresh rate selection and understands the whole pipeline. So we will go through 4 different sections in this presentation. One is like the selection, which is basically how we make the refresh rate selection for the current composing layers and everything on the Android operating system. Then we will walk through 2 different displays which are currently under VRR in VR section. Then we have frame pacing, which is basically how you manage the frame timing for different refresh rates, how you get callbacks and things like that for the rate that you want. And then we will go through some verification techniques, how you can verify that you are actually getting the rate that you want. So to begin with, we will slowly feel this diagram where you have an app on the one side and the Android framework in middle, and then there is a display hardware. So we'll fill in the details how an app makes a request, and that request comes to the display when you present your frames, how the refresh rate and everything gets connected. So let's start with selection. So so this is for the apps. Like we have wide variety of apps and games on Android. They range from fixed frame rate, like one that uses Android toolkit like buttons and all of that. Then we have games which don't use any of those components. There are different game engines and all of that, right? On top of that, we have wide variety of Android devices. Some of them have different refresh rates, some of them have different shapes, like ordering kiosk and things like that, or mobile phones, infotainment systems in airplanes, and all these kind of devices. So we have to be mindful of all these different kind of devices and apps they are running on them and manage the refresh rate for them. We have apps which generate consistent frame time, which is basically they have fixed frame rate and they can generate a frame at that fixed cadence that they want to run at. Or we have apps, they don't have any consistent frame rate. They don't know what frame rate they can target. So we have those kind of apps as well. So as an operating system, we have to make sure that some of these requirements can be met and people can actually do their programming on this. Then we have device constraints. Not all devices are equal. Android supports a wide variety of devices like we talked about. And these devices have different constraints. Like they can be permanent constraints or they can be temporary. Like power savings mode is a temporary, and or high brightness mode. But some of them are permanent as well. Like a device might only support one refresh rate, or they might support so many refresh rates but with limited conditional approaches. So let's start with an example app. This is a bouncy ball example app, which just has a ball that moves around the screen, and it has a slider for refresh rate selection and different modes and things like that. So if we consider this app, so there are certain ways we can set frame rates in Android to achieve what rate we want to achieve. So some of these are like window manager, which is an Android system level component, or on a surface. You might not be using any of these window manager. You have your own surface on which you draw things, and you can set frame rate through that. Or you have a surface control acquired, and that also supports transactions to set frame rate. So support wide variety of apps and their requirements. There are many different ways we can set these. And if not anything, if you're using Android toolkit components like buttons or image view, anything like that, you can also do that on the views with set requested frame rate. So if you have a GIF, you want to control and display it on some view. But if you, let's say, are not on the Java side or Kotlin side or any of the app sides, you're on the native side, writing C++ or Rust app. So similar kind of methods or functions exist for the native side as well. So same for the surface control transaction, we also have a native side for it as well. And so what this does, when we set the frame rate, it sends a signal to the Android framework that an app is targeting a specific frame rate. And these signals are used for constant frame timing and Android operating system, which is basically tied to the display vsync. So because we cannot present at any moment, we have to be mindful about what vsync the display is running at, because at the end, that's what matters. And by setting these frame rates and all of these, there are certain features like frame rate override which are possible, which we'll see an example of, where we can run at some of the divisor rates of the actual vsync. So even if the display does not support the rate that you want, you still can run at the divisor of that refresh rate. And let's say there, in any case, like none of these APIs work for you because you don't have frame rate. We still have certain APIs which are supported for the EGL or for Vulkan games, or you can set a desired present time through which we try to map that to the vsync and present it as close to the vsync that is possible around the desired present time that you want to present at. All right, so we have this app. Now we know that there are set frame rate functionalities and everything. So in our example app, we use this window manager layout params preferred refresh rate and ask for the 120 hertz refresh rate. So this is how we made that call over here. So what happens when we make that call? What goes on in the Android framework? So Android framework sees all these different layers on this display. We don't even see them, some of these by our eyes. But not all of these are important. The ones which are important are the only ones which are visible, and they have certain vote or certain opinion about how they want to run it. So we filter these out. So under the layers, once the app is done, the layers that we receive in Android operating system, we filter them out like this. So, but we got the layers, we sorted them. So this is like the bare minimum extraction and aggregation of these layers and votes. So once we have, like the bouncy ball, we set the rate that we want is 120. The status bar and taskbar don't have much of vote because they only vote, like they are mostly static until something notification, something pops up. So what happens once we have these votes? We have frame rate. So based on what rates we got, we use these signals from the set frame rate and do the scoring of each of these refresh rate, different refresh rates that are possible in the operating system. So if let's say 120 got the highest score over here, which is 1, is because we requested for it. There is someone who is asking for that rate. So we get these signals which are used to make these, but you see that there are other rates which are also scored. Why do we score if someone only wants 120? We'll see that very soon. So what happens here is we select 120 because it got the highest score. So these scores considered are used, different parameters are used to decide this. One is like the weight of the layer, the size of the layer, things like that. So there are certain parameters which are used. So let's make this example slightly complicated because that was too easy. So now we go back to the same app, but we add a new window to it, which is picture-in-picture mode, which shows a video over here. So we also change the refresh rate of our bouncy ball app to 60. So previously it was 120, now it's 60. So it's changing its vote. At the same time, video that we are running at is 24 FPS. You can see that they are not multipliers of each other. They fall on different timelines, but they do have some overlapping time on the vsync timeline. They do have some overlaps. Every other vsync will overlap between 60 and 24. So what Android does in this case then? So we still go through the same process of having the same layers which are visible on the screen. Now we have one additional layer which is picture-in-picture pip window. And this is some kind of information that is like extracted, and this is the bare minimum information that we can see that these layers vote for. Now when we receive these different layers, we, in the scoring section where we do the scoring, we actually score them separately first, so that they can rate whatever their preferred rate as, and their multipliers the highest. So you can see over here like 24 FPS actually gives a score of 1. It gives a score of 1 for 120 as well as for the 24. And it also votes with the type, which is exact or multiple, that you can see here. This information tells the Android operating system that I'm okay with anything that is 24 or multipliers of it. And on the 60 side, we see that 120 and 60, they both got 1 because they are multipliers of each other. They can run at both at 120 by skipping a vsync or run at 60 by rendering at every frame. So how do we satisfy both of these? So we look at both the scores and we see that they both have 120 scored highest, which is 1 in this case. So that's why we end up selecting 120 here and satisfying the requirements of both the apps. So this layer scoring helps because this only works because we set a frame rate on it, and we can create a frame rate using this. So where in Android all of this is happening, which for the refresh rate selection, is something called Surface Flinger component, which is like the hardware all of this is happening. There is a refresh rate selector, there are schedulers and things like that to make these selections. So Surface Flinger is a very important component in this case because it is like a system compositor which takes all the surfaces and does all the calculations that we just saw, and also presents them on the display as well. So this is where all the layers from the system components like window manager or any other status bar and everything comes from their system UI. And any app transactions can also be used to manipulate the layers on it, like set frame rates or change any of those properties or geometry or anything. And it sends the signals to the composer HAL, which is on the display side. So it crosses the boundaries from software side to the hardware side through the composer HAL to send the present the surfaces on the display. So now we understand that in the app we did the set frame rate, we did the scoring of the layers, we selected the refresh rate, but we have to also understand what to do with that refresh rate. This is where the type of the display comes in picture because the frame rate is only half of the picture. So in VRR, we have two different kind of displays. One is MRR and one is ARR. So this is our display, let's say, for multiple refresh rates. So what happens in that? So display comes with an MRR with two, let's say for our example, let's take two different display modes. So one that supports 120 Hertz refresh rate, the other one supports 60. There can be many more. In here we are just going with 2. So what does display mode means here is, so when we switch to the mode 0, the display vsync rate changes to 120. Or when we switch to 1, the display vsync rate changes to 60. So it actually changes the rate at which display is working at. So this is a mode change at the hardware level. So in order to change the refresh rates in MRR, we have to switch the modes, which is a request to the display side, hardware side. So Surface Flinger, once the refresh rate selection is done, makes the request to the hardware, hey, we have a refresh rate change and you need to change the mode, the one that supports this refresh rate. So in our case, it will send the signal that, hey, I need a 120, the mode with a 120 refresh rate, because we have 60 plus 24 that actually resulted into 120 that we can run at. So there are few things with this kind of like mode switching where we can achieve multiple refresh rate or a higher refresh rate or lower whenever we want them. So these mode switches can be indeterminate. What that means is we can make requests to change the mode, but hardware can take different amount of time on different kind of displays to switch the mode. It might take 1 vsync, it might take 2 vsync, so it's not predictable when it will do that. So that makes the software side also unpredictable in this situation where we want to make this switch. So this switch can be tricky to achieve with a smooth transition without actually creating a jank. And so far we saw like the 120, 60 or 20 up to 20, but always on display is a special case. Is because like these always on display is a mechanism where your display is almost off, but it has some kind of information like a clock and things like that displayed on it. And these modes are usually like 1 Hertz mode. But if we have to make a switch from 1 hertz mode, it can be very tricky because the latency can be very high. So because of this, these modes are handled directly under the HAL. That means the Android operating system sometimes don't even know about these modes. And that's why these kind of modes are like filtered out by the OEM manufacturers sometimes to avoid having a longer latency. So let's say you are refreshing at 120 constantly, but suddenly nothing is happening now. You received a notification or you were using your phone to scroll, but now it stopped. It's a wastage of power to keep refreshing the display at 120. So what we do is like, there are like different kind of idle timers implemented. They wait for a certain time. If there are no updates, it automatically switches the mode to the lower refresh rate to save the battery. So this is what we saw, and all of this display modes and everything that we saw was on display hardware, then the Android framework. The information that the modes exist, different kind of modes exist, and what Android operating system has access to these modes is exposed through the HAL, which is hardware abstraction layer, which is basically an interface implementation that is done on the software side, as well as the implementation is done on the hardware side. So that interface helps us communicate with the hardware side. So these are like the binder calls that goes from the software boundary to the other side where the hardware composer implementation is done to query these parameters from the hardware. Now let's switch our focus from multiple refresh rate MRR to ARR. ARR is very recent, it's very new. And the best part about it is we don't have different modes. We just have one mode. I mean, you can have multiple modes with just very high refresh rates, but it's not required at all. You can have one mode that supports 240 hertz refresh rate, vsync rate, which is very high, and you can just run into it. Run with that one mode, you don't need to switch any of these. So how does it do all other refresh rates? So we'll see that. So display can present at any of the divisor rates of this 240 hertz vsync. That means you can present at 80, you can present at 60, 48, 40, any of these divisors. So you can select any of these refresh rates on this display and it will be able to present without switching any modes. Though there is a catch. 240 is really high and it consumes a lot of power, and also there is a delay between scan times. So display also has to scan line the whole display and present every frame. Because of that, there is like a capped max refresh rate that is there. Like you cannot cross the boundaries of that max refresh rate, even though your vsync rate is too high. And this changes the way it runs, it changes the way refresh rates work. So this makes the render rate switching predictable. In MRR, we saw that the changing the mode was not predictable. It can change at any time, and that makes software side hard. But here we are changing because there is no mode change, display is always running in the same mode, it's easier to change between different refresh rates. And we don't need here any idle timers or anything to achieve when user is not doing anything. The reason is because there is something called step down, or like the display itself slows down internally and it automatically goes towards 1 hertz mode. So we don't have to do that from the software side or do the mode switch. It is automatically handled inside on the display panel itself. So there is more extra power savings because we are not making any of these binder calls or anything. So this automatically becomes easier to work with in these terms. And it's also more power efficient because we can actually run at lower refresh rates. So let's say you are scrolling, and when you scroll, you are at 120 in the MRR all the time. Because if we switch in between, like I said, it's unpredictable. It will make your scrolling look janky, it will jumpy. But over here, because there is no mode change, you can actually switch to a lower refresh rate if you want to while scrolling, and that will actually, as you slow down, you can change the refresh rate to be lower and it will be smooth. So that's how it runs at lower refresh rate far more than the MRR counterpart. So we saw that MRR display, mode switches and all. So let's take an example of ARR with 240 Hertz with a max refresh rate of 120. So now consider this as a VSync timeline. This is our timeline, and this is 240 Hertz, two VSyncs, 4.16 milliseconds apart. So if we present at the very first VSync, because we are capped by the max refresh rate of 120, we cannot immediately present because that VSync is blocked. But we can present at 240 divided by 2, which is 120 Hertz. And using this, we can achieve 120 Hertz refresh rate. Or we can present at 240 by 3, which is 80 Hertz. Or at 60 Hertz. Or at 48 Hertz. So these all possible presentation times are possible with ARR just by dividing the original VSync rate of the display. So what majorly differentiates between MRR and ARR, one point is like peak refresh rate is different from the display VSync rate. That was not the case with MRR. So in multiple refresh rates, we have a mode. Once we switch into it, VSync rate, peak refresh rate, everything is same. So if we are at 120, it's always 120. But over here, peak refresh rate that is achievable is different from VSync rate. Display might be at 480, but if it says it can only do 120, software has to understand that it cannot cross those boundaries. So in MRR, what content drives the frame rate means is like in MRR, once you switch into a mode 120, it's always refreshing at 120. Even when you're not presenting a frame, unless it switches the mode, it's always like refreshing the content, even if it's presenting the same buffer. But over here, content drives the frame rate. That means if there is no new frame or anything, we can tell hardware like there is no frame, so it starts the step down and it actually goes automatically to the lower content rate. And all these implementation details of MRR and ARR are actually abstracted from the end developer, so you don't have to care about all these implementation details. These exist so that you understand why we need set frame rate, what benefit it provides on different platforms. In order to support this, we obviously need a new HAL, which is basically all the hardware manufacturers need to implement new APIs, because if the content is controlling the rate, we have to somehow tell them when the content changes the rate. If we don't tell them, they don't know. So that was the part where how displays work. And first we went through how the refresh rate selection is done in Android operating system. Now we have these pieces together that we did the refresh rate selection, displays handled. Now comes the frame pacing. So we initially saw we have an app that runs. So how do we know when to render from the app side? This is where frame pacing comes in picture and something called choreographer. This is a public API, has been a public API for a very, very long period of time. This API can be used for getting the consistent time pulses mapped to the frame rate. So whatever the frame rate your app is requesting or the display is running at, you get a callback on that timeline. So you can take advantage of the implementation of the Android frame rate selection and the VSync and get mapped to it. This provides very fine-grained control over the frame rate, and we will see an example of that. All right, so this choreographer provides you with an opportunity. This is a very nice API where like when you post a VSync callback, it provides you with possible frame timelines. What that means is you don't have to pick the very next VSync that you want to present at. It provides you with multiple choices. You can pick any of those choices to present at, and you can use that. And it also provides frame deadline for each of those possible VSync timelines. What that means is your frame from your app should be ready by that time. And then expected present time is also provided, so that way you know when your frame is going to be on the display. So we talked about one of the benefit of frame rate override before. So what that means is, instead of, let's say you have a 24 FPS video we saw in our example, and another screen was 60. It's a wastage of time or the processes if I tell you that we are going to give you callback at 120 all the time. because it makes no sense. You want to run at 24, even though the display is at 120, you want to run at 24. So this is where Android operating system can throttle the vsyncs for you so that you get callbacks only when you need it, like 24 FPS, not on every 120, and then you can simplify your app side. Yeah, so you simplify your frame pacing logic on your side, so you no longer have to identify that either this vsync is for me or not, because Android does it for you. And this saves a bunch of power, because now we are not doing unnecessary composition or callbacks, binder calls, or any of that. So everyone gets the power savings because they get the callbacks or the timing for the rate that they need. And this benefit actually works on both MRR and ARR. So even if, like we said on MRR, the display is always refreshing at 120, that's fine. But if your app requests like 30 on 120 or 24, you get callback only for the vsyncs where you want the rate to be 30 or 24. So you get the power benefits in both the displays. So you no longer have to manage any of that. So if you're not using Choreographer, but you want to use something which is Android frame pacing library, which is Swappy. So Swappy helps with certain games and things like that. So this is part of the Android game development kit. And this can be used for frame pacing in a similar fashion the Choreographer can be used. This can be used with OpenGL or Vulkan games, so it supports both of those games. So when you do the EGL swap buffer or VKQ present KHR, this automatically swaps the buffers on the screen for you and manages that frame pacing for you. So you no longer have to manage this frame pacing. And the good thing is, like, this uses the very stable APIs of Choreographer, so that it relies on the similar APIs which already exist. So it does not bypass any of those systems. So that way, it is very reliable as well. So let's connect the dots now. So we did the refresh rate selection. We know how the displays work. We did the frame pacing as well. But how all of these pieces fit together? So this is Android framework. We have display hardware. Then we have the scheduler Surface Flinger, which does the refresh rate selection and all that part. And we have hardware abstraction layer that talks to the display and bridge that gap for us. Then we have the app. Now app uses either the Choreographer directly or some form of like Swappy or anything or instance, or it uses the toolkit components. And that's how it sets the frame rate or uses the frame pacing from this side. That information comes to Surface Flinger. That makes the refresh rate selection, handles the display mode changes, everything for you. And on the return, when you use frame pacing library, you get the callbacks from the Choreographer or toolkit. Toolkit components uses Choreographer internally, so that way you don't have to handle that. But you can get callbacks from the Choreographer if you want a fine-grained control over when you want the callback. So this is how all these pieces fit together. So last, we can move towards the phase where we can verify how all this information is working. Like, you set a frame rate, but you need to verify that it's actually working or it's giving you the rate that you want, because otherwise you will have other issues. So there is a setting in Android developer options, which is refresh rate indicator. The name can be changed by OEM because whatever they feel is. So this shows the aggregated refresh rate, which is like basically what the display is running at. Even though your app might be 24, like we saw, we selected 120, this will actually show 120 instead of 24. So this is actually the display aggregated rate. So that is one way of verifying the information. But other way is you can verify on your own in your app. Like this Bouncy Ball app actually has its own refresh rate that is being calculated as 120 in between the calls. So what it does is, like, it does the Choreographer callback, and then it gets the callback back, and it counts the difference between them. So that's how you can measure on your own how the frame rate, what the frame rate that you are getting. It's not me. So if all of that is too much, then I have few takeaways to make it simpler. Not everyone has to go through all this display and all of that. So the takeaways is use the set frame rate API. It creates a very consistent frame rate signals for the Android operating system, and it creates the refresh rate selection process very simple and consistent and reliable. The other one is use any of these frame pacing libraries for consistent frame timing when required. If you're using standard components, great, it automatically does it for you. But if you're not, if you're building or rendering on your own, use one of these, like either Choreographer directly or use the Swappy and manage that. It will be actually much simpler. And always verify the frame rate that you are getting, because sometimes we think that it's working, but it's not. That's where use the verification techniques of either refresh rate indicator or measure it yourself. And that way you can be sure that you are actually getting the frame rate, because indicator might say 120, your app might be 24. So you should measure that it's actually 24 that you are getting callback at. 120 is because someone else is also there on the screen with your app. So that's adaptive refresh rates on Android. If you have any questions, you can ask me now, or you can email me at ramindani@google.com. So now, or anyone? Yeah.
Question on frame pacing for very challenging scenarios. So if you have like a partially blended background with a UI up front, how does adaptive refresh rate and the swappy layer deal with it? The background is only being rendered one in every 3 frames, and so the load for one in every 3 frames is much higher than the other two. Does ARR and swappy prioritize like keeping the frame rate very high for the 2 frames where the load is very low? And or does it prioritize just a generally low refresh rate to manage the like very high requirement of the background being rendered?
Yeah, so let me repeat the question so that you can verify I got it right. You're saying if, let's say, one of the screen or frame or layer is rendering at low refresh rate, but something else is higher, then how does MRR or ARR manages the frame rate?
If the refresh rate is not defined,
Refresh rate is not a divisor, you said?
it's not defined by the user anyway. They're just submitting frames.
Okay.
So 1 in 3 frames is significantly more expensive because they're doing significantly more rendering work.
Okay.
Is
Yeah.
there additional work by Swappy and AIR to handle this?
Yeah, so we do have something which is called heuristics in Android. When we don't have any rate or anything, we actually find out how much the difference between 2 frames is, and we learn that this is the rate that probably you wanted. So we constantly learn that, and we try to manage that and select a refresh rate for you if you don't have any rate and you don't know what, and if you are just submitting buffers. That's how it's managed. But there are catches with that. The problem is, so for example, let's say you're running an animation, then there are constant frames. It's easy. It can get to 120 and stay there. But when you are not running an animation, you have one-off updates like that. We switch to, in MRR, we sometimes switch to 120 because we want to immediately present your frame if it's closer to the expected present time or desired present time. On ARR, we don't need to switch modes. What we do is, let's say that 60 plus 24, right? It's kind of similar. So it will present 60 every 16 milliseconds. One of the frame will overlap with 24, but when it does not overlap, it actually presents the frame immediately in 8 milliseconds for 2 frames, because that way, when 2 frames don't align for 24 and 60, it can still match that. But if it's MRR, we keep it all the time on 120. And that way, because it's on 120 all the time, the framework will wake up and see that there are no buffers because we have frame rate override if you use the set frame rate. If you don't, we don't know what rate you want, so we cannot frame rate override you. Does that answer your question?
I think so, yeah. I was wondering mostly if ARR has a way of noticing that the frame rate is very different between frames, or the frame workload is very different between frames. And it seems like it would basically present twice on a higher refresh rate for those cases.
Right. In a way, yes, that's exactly what it does. Yeah. There are tools to visualize that, actually. Yeah.
See if there are duplicate frames.
Two things. One is if you have a duplicate frame, probably that's on the display side. There might be tools for that, but I'm not aware of that. But there are a few other tools where you can see when the frames were submitted and all of that. Yeah.
Thanks.
Any other questions? Yeah. If you want to see that tool or anything, I can show you that tool after our presentation. How it runs on, like how 60 and 24 gets rendered on the frame timeline.